Let's ask ourselves, does the sum from n from 2 to infinity of 1 over the cube root of n squared plus 3, does this series converge or does it diverge? And so what we're going to do, we'll use direct comparison test. And so we're going to end up showing, let me label this as a goal. We want to show that this series of inequalities is true when n is at least 2, because that's the start. We're indexing starting at 2 here. And so as a result, so this part is not clearly true. 1 over n is, for n is greater than or equal to 2, that's going to be strictly positive. So the interesting thing is going to be examining this. Let's cross multiply to say this is equivalent to n squared plus 3, the cube root of that is less than or equal to n. If we cube both sides, n cubed plus 3 is less than or equal to n cubed. We move this to the other side, we get n cubed minus n squared minus 3 is greater than or equal to 0. And so we can check here, if we're thinking of, if we convert the n's to x's, f of x is x cubed minus x squared minus 3. The derivative here is going to be 3x squared minus 2x, and we can pull out a factor x times 3x minus 2. Minus 2/3 if I pull out that 3x there. And so this is positive for x is greater than or equal to 2, and f of 2 is equal to 1. So what's our conclusion? This function is positive at 2. The derivative is positive, so it's for x is greater than or equal to 2, so this is increasing. So this is greater than or equal to 0. For n is greater than or equal to 2, chase it all the way back. This inequality, we can satisfy it. Okay, so far so good. Now we're going to, let me get a fresh sheet of paper here. Now we are in business to be able to apply the direct comparison test. Because we're going to, let's see here, we've got 0. So 1 over n is going to be our a sub n. 1 over the cube root of n squared plus 3 is going to be our b sub n. And so we know the sum from n from 2 to infinity of 1 over n, this diverges. Once again, that's our p-series test here. We don't worry about whether this starts at 1 or 2. Initial terms won't make any difference. So by DCT, direct comparison test, because we have that 1 over n squared plus 3, the cube root of that, is going to be bigger than 1 over n, so this must also diverge. So this is what's going on. In the previous video, we used this case. If the series, the sum of the bigger terms converges, the series for the smaller terms also converges. Now we just showed that the series for the smaller terms diverges. So by the direct comparison test, the series for the bigger terms also diverges. Okay, one more application that's going to kind of mix together a couple things here. The sum of 1 over n, and also a square of the natural log of n in the denominator. So something that we might be tempted to do is to compare this to 1 over n. So we might think that this is the way to go, but the integral from 1 to infinity of, oh, sorry, not the integral, the sum from 1 to infinity of 1 over n, this diverges. This tells us nothing. Why is that? So if we know that the series for the bigger terms converge, we know that the series for the smallest terms also converges, but this tells us that the series for the bigger terms diverges. That doesn't tell us anything. If you're smaller than something that diverges, you might diverge, you might converge. It doesn't tell us anything. So we've got to think about something else here. Instead of using the direct comparison test, we are going to instead use the integral test. So we're going to integrate from 1 to infinity, 1 over, we convert the n's to x's, x over natural log of x squared dx. We have to do our standard thoughts to make sure that 1 over x times natural log of x, that's continuous, it's decreasing, it's positive. It checks all of that. So when we carry this out, limit as r goes to infinity, 1 to r of 1 over x, natural log of x squared dx. And this is going to be a good one with integrals because u is natural log x, du is 1 over x dx. And this all checks out. Everything is taken care of. So when x is 1, u is 0 to natural log of r of 1 over u squared du.